That last name is pronounced Euler, not Euler. I know it kind of looks like Euler, but it's Leonard Euler, who is a brilliant mathematician from Switzerland. In fact, Leonard Euler was the one that discovered E, 2.7, 1828, 1828, 4590, 4523. That's him. He named it after himself. That's why it's called E. I'd name it after myself if I invented something that cool. Of course, I wouldn't call it E, I'd call it L. But anyway, Leonard Euler also came up with a method for estimating solution curves. Like I mentioned in the last lesson, a lot of times you have a differential equation in real life because you can measure, the speed of an object or the rate of change of a chemical reaction. But the object itself, the bird that's flying through the sky or the chemicals that you're working with in the lab, they don't have equations for themselves. So you just measure reaction rates. You measure the rates, the derivatives. And then you piece the derivatives together in a slope field, and sometimes you can see where the original curve would be going. You can kind of guess at an equation. Sometimes, however, you need to know, like, say, a y-coordinate. Let's say you know for sure that this blue graph goes through the point 2,1, but that's all you know. And you know that its derivative is x plus y, because you can measure that a lot more easily. But let's say you're concerned more about, hey, where is this blue graph going to be when we get to point 2, 6? Well, Leonard Euler came out with a way to figure it out. And what he did is he used slopes along the way and came up with this method. And I'll show you the method right now. It's really cool. Okay, so I based this problem off the graph that you just saw. Same derivative, x plus y. It went through the point 2, 1, so f of 2 is 1. You can see that I have 2, 1 in the very first cell of the chart. And I want to approximate f of 2.6. What's the y-coordinate at 2.6? They will tell you how many increments to use or what the increments are. So in this case, you can see it says delta x. Remember, delta means difference or change in. Delta x is 0.2, and I have that right here. And by the time we get to the lower right corner, we're going to have our answer. All right, this is pretty abstract, so I'll see what I can do to explain it. We start with the point xy. By the time we get to the end, we're going to have a new x comma y. I know that this point will start with 2.2. I don't know what the new y-coordinate is. The reason I know that is I keep adding 0.2 on every time. That's the delta x. I know that this is going to be 2.4. And then below it's going to be 2.6, which is what we're trying to figure out. And the answer will be right here, the y-coordinate, f of 2.6. I can come over here to the left and do the same thing, 2.2, 2.4. As soon as I know what this is, right here in red, I can copy, cut, and paste it down here. And same thing for the 2.4. As soon as I know what this is here in green, I'll just copy it down here. Okay. The premise behind this is if you know dy dx, which we do, and you know delta x, which we do, if you multiply them together, you're going to get delta y. Let me show you why that works. I'll try to find some space up here in the corner. If you have dy dx, dy dx is high school slope. It's the derivative. You also have middle school slope. And middle school slope is just rise over run, or change in y over change in x. It's that good old y2 minus y1 over x2 minus x1. Remember, delta means subtract. What if I took this equation and I multiplied both sides by delta x? Well, the delta x's would cancel, and you would see that delta y is equal to the derivative times delta x, which is exactly what we have here in Leonard Euler's method. Okay, enough of me babbling. Let me take you through the chart. This is a lot easier than what I'm making it sound. Okay, we have the point 2, 1. Let's plug that in. X is 2, y is 1. The derivative is going to be 3. All right, let's multiply the two columns together. 3 times 0.2 is 0.6. So the y-coordinate went up by 0.6. It started out as a 1, now it's a 1.6. Take that 1.6, bring it down to the next line. All right, let's repeat the process. This time we'll repeat it in green. X is 2.2, y is 1.6, making the derivative 3.8. .8 times 0.2 will be 0.76. You're allowed a calculator on this, by the way. All right, the new y-coordinate would be the 1.6 we started with, plus an additional 0.76. That'll be 2.36. And that goes down here as well, 2.36. All right, finally, last line. dy dx, the derivative is just x plus y. If you add these two things together, you're going to get 4.76. Multiplying that by 0.2 is going to leave you with 0.952. Adding the 0.952 onto the pre-existing 2.36 gives us our answer of 3.312. So therefore, f of 2.6 is about 3.312. Remember, it's an approximation. If you didn't think that was too bad, that's good, because College Board never has 3 rows in their problems. They only go to 2 rows. I've never seen them go above 2 rows, at least not yet. Hopefully this won't be when it starts. All right, let's try another one. This time the derivative is 2x minus y, and the original point is 2, 3. I want to know what happens at the point 1, 7. That's where I want to end up at. 1, 7, comma, what is this? So I have to figure out what my delta x is. They told me to do equal increments, so I must be going down by 0.1 each time. That would take me from 2 to 1.7. All right, let's get this figured out. This is going to be a 1.9, a 1.8, and obviously my 1.7. Let me copy that over here. 1.9, 1.8. Okay, looks like we're ready for action here. All right, we'll start with the 2, 3, and it goes. That's going to be 4 minus 3, that's 1 for the derivative. 1 times negative 0.1, of course, is negative 0.1. So the y-coordinate goes from 3 down a little bit to 2.9. 2.9. And I will copy that into the next row. All right, let's try this again. Again, up here, we double the 1.9. That's 3.8 minus 2.9. That'll be 0.9 for the derivative. Multiplying the next two columns together is going to be negative 0.09. If you add that to the 2.9 we started with, the new y-coordinate becomes 2.81. And again, these will go up into here. You double the 1.8 to make 3.6. Take away 2.81. Obviously, you probably want to use a calculator at this point. It comes out to 0.79. Multiplying that by negative 0.1 will be negative 0.079. And finally, our answer, 2.81 minus 0.079, will be 2.731. So f of 1.7 is about 2.731. Now here's what's interesting. We used 3 equal increments, but if we made the delta x smaller, much like with trapezoidal rule from chapter 4, much like LRAM, RRAM, MRAM, the more rows you have, the better you're going to be. The actual answer to this is 2.7498. So we weren't too far away. We got 2.731 with minimal work. If you figure out the error, it's less than 1%, which is actually pretty stellar. Usually in a science experiment, you're pretty pleased if you get an error less than 1%. I want to show you, using Microsoft Excel, how to get a super accurate answer for Euler's method. Okay, I'm here in my own Excel spreadsheet that I made, and I'm going to show you how to program. I'm going to do the same problem. I'm going to try to find what f of 1.7 was. My answer is going to be down here in this last cell, the purple cell. All right, I have my original point, 2, 3. dy dx is 2x minus y. Anytime you're in Microsoft Excel, you say equals, and that tells the program that you're going to actually have a formula. I want to go 2 times cell B5, so that's 2x, minus the next cell over. And then I'll calculate it for me. All right, let's go over to here. Delta y is equal to the two entries right before me, this one, times negative 0.1. Okay, x plus delta x. So that's going to be equal to what I started with, which was this 2, plus whatever's in the delta x column. Y plus delta y is going to be equal to the original y, that's the 3, plus delta y, which is right here. If I go down to here, I can go equals this, equals this. That way I've sort of done a cut and paste. And I should be able just to fill down the rest of the way. Control D, Control D. Let's fill this all down. I'm going to lose my purple, but that's okay. Yeah, there's my answer, 2.731, the same answer that we just got. As cool as that might be, you know, we only did 3 steps. We went by 0.1 or negative 0.1. What if we went by negative 0.01? We'd get a much more accurate answer by the time we were done. Obviously, a lot more work. That's why Microsoft Excel is so cool. There's an improved answer of 2.7478. If I went by negative 1/1000ths, you'd get an even better answer, although it would take a while to add it all up. Leonhard Euler in Switzerland didn't have this technology. There's 2.749. And finally, if you went one more decimal, you're going to get a much better answer. Ooh, it's making me dizzy. Wow. Again, anything that you would misadd would ruin everything else. So obviously, in the Middle Ages, this wasn't possible. Ah, there was the answer. 2.7498 is going to be pretty close. 2.74977. Okay, great. So you can see that's where I got this from. So 2.731 after 3 steps isn't too bad, but if you want to get more exact, just make this smaller. What that'll do is in this picture, this is delta x right here, the distance between these dotted lines. If the lines become smaller, the slopes get a little steeper and the estimate stays closer to the curve. The gap in between here doesn't get as large. It doesn't sort of fray away from the real answer quite as quickly. So that's Euler's method, figuring out y-coordinates simply by using derivatives, rates of change. Here's one more Euler's method example problem, just a different way to kind of present the problem. This time I did not include a table. We'll have to make our own. Not a big deal. But it says use Euler's method starting at x equals 3 with 2 steps of equal size. So we'll have to figure out what our delta x is going to be to approximate f of 4. Well, if we're going from x equals 3 to x equals 4, I think you can see that our step size has to be 1/2, so that's the delta x. Let's go ahead and create the table, and we'll fill it in and get an answer. All right, we're going to go ahead and start with the point 3, 2, since they've given that to us. And we know that we end up down here with a 4, answer. So that means that we're going to have a 3.5 here as our sort of midway point, if you will. Let me copy that down in the lower left. And as mentioned, our delta x has to be 0.5 or 1/2 both times. So we're sort of starting to fill in the table bit by bit. Let's see what happens next. We'll get our dy dx's. All right, so 3, 2. In goes the 3, in goes the 2. That's going to give us 3 plus 2, 1/2 of 4. So that's 5. And 5 times 1/2, moving across, because remember, dy dx times delta x gives us the delta y. So we multiply those two middle columns together, and we get 2.5. 2.5 is what I add on to the original 2, so that's going to make 3.5, 4.5. We'll bring that down. All right, this is going to get a little trickier plugging that into the derivative. Let's see, the next derivative, x, that's 3.5, plus 1/2 4.5 squared. 4.5 squared is 20.25, so half of that would be 10.125. All right, so we have 3.5, put a few zeros there, plus, I said 10.125. That's actually not too bad to add. That's going to end up being 13.625. Whew. Cut that in half. Let me get a calculator here, just to be safe. 6.8125. 6.8125. We'll take that and add it on to the 4.5 that we already had, giving us an answer of 4, and here it is, 11.3125. So f of 4 is approximately 11.3125. By the way, that happens to be 11 and 5/16 as well, if you want to write it as a mixed fraction. If you don't like mixed fractions, it's also 181/16. All of those are fantastic answers. Any one of those would be completely fine. And that's it for Euler's method.